So we're going to switch gears a little bit here. So what we've heard in the morning was people using CFD or Barracuda to solve real problems, to look at real problems, and we looked at very specific problems. The CPFD folks, or I'm sorry, the CPFD 2.0 folks asked me, I said, well, can you talk about how PSRI actually uses Barracuda? All right, so that's basically what we're going to talk about, is basically how PSRI streamlines our work process by using the Barracuda Virtual Reactor software. Most of you kind of know who PSRI is. I'm just going to review it a little bit because it does apply a lot to the context of this talk. So we're a research consortium. We've been around since 1970. We were father of PSRI is Fred Zenz. And the goal here was just to do research that was industrially relevant. Now, when you're doing granular fluid flows, especially gas solid type of flows, size matters. All right, when you do things in a very small size, the wall effects alone seems to dominate everything, and now you're trying to scale up with that, and you realize that you've missed the boat quite a bit because of that. So experiments tend to have to be done on a very large scale. All right, and that's where PSRI comes in. So we sit on about 5 acres. We have about 11 buildings. 2 of our research labs are very high. One is 55 feet high, the other one's 130 feet high. We have a circulating fluidized bed unit that's 90 feet high, with the risers actually 3 feet in diameter, 7-foot diameter fluidized beds. We do things on a very large scale. On top of that, we have a lot of consultants. Okay, we have a battery of both consultants from in-house and external consultants that are all experts in the fields. And we do a lot of training. We teach seminars all over the place. We have tutorial modules. We have also a wide range of design guides, all this to help with respect of the membership and sometimes with beyond the membership. So as you can imagine, doing all this gets expensive, right? Because we're not doing anything on the benchtop. Everything's done on a very large scale. So the way we have to get around this is we have to trying to figure out how we parse everything out. So first of all, we have experts. Okay, we have about, or knowledge, we have about 200 cumulative years of experience within our experts. All right, and we're world-renowned for our expertise in fluidization. All right, we have state-of-the-art facility with large-scale experiments. We have not just the size of our buildings and our units, but we have the blower and compressor capabilities to make all that work. I pay the electric bill, so I'm well aware of that fact. So we also have some of the best people in the world that have worked in this area for a very long time. All right, and so if we don't know the answer, which we probably do, we've probably seen it, but if we haven't seen it, we actually have the facility to actually figure it out. So that's what makes us unique. We're not truly consultants, and we're not truly just doing academic research. We're actually somewhere in the middle where we try to do it all. All right. As a result, we have over 30 terabytes of data on our file server, something my IT guy, Matt, is not very happy about, okay? And if we put all that together, we provide research, consulting, and training, all right, which gives us a nice little package for helping to design, solve real-world fluidization problems. Here's a list of some of the things that we have been involved with. This is a list of our current consultants. Dr. Reddy Carey, Ted Knowlton, myself, and Ben are all with PSRI. Greg Mihos, if you were here yesterday, Greg Mihos gave a workshop on design of bins and hoppers. He is probably a leading expert in that field. Manuk Kalakian was one of the researchers involved with the Unipole process and the invention of the Unipole process, knows more about polyethylene than anybody I can think of. And on top of that, he switched gears about 10 years ago, so now he even knows a lot about supercritical fluids. So it's an interesting combination. If you ever work on cyclones, his name Mush Canales should be very familiar to you. Okay, he's also on board with PSRI. And then we recently just signed CJ Farley, who has worked on over 200 FCC units alone, all right, and pretty much can solve anybody's problems in these units. As a result, we have worked on various types of projects, from acrylonitrile, catalytic oxidation, chemical looping, dehydrogenation, including propylene dehydrogenation, maleic anhydride, oxychlorination, polycrystalline silicone or high purity silicone, sulfur capturing, CO2 capture, biomass. We've seen it all. The problem we have is that all this gets very expensive. Experts are expensive. Research in the laboratory is expensive. Even going out and training all over the world is expensive. All right? So we have to actually figure out how to put all this together. And that's kind of where we come up with this R&D process. All right? So we have a problem. We have a hypothesis for this problem. All right? And that's pretty much depending on the experts talking about what's going on here. All right? And we may have more than one answer what's going on. All right? Then we use modeling. All right? Most times it's Barracuda modeling. All right? And we define that research space. Okay? We narrow the pool. Classic example is, let's say the problem has to do with a sparger design. All right? I don't really want to put 5 or 6 different sparger designs in my unit. It would get very expensive. I like to just do two or three. All right? So we may use the CFD modeling to actually reduce that down from 5 or 6 to 2 to 3. All right? That cuts our cost down by 30%. All right? Then we do the research. Now, we're an experimental outlet, so we do the experimental research. All right? And then we go back to analysis. Now, with analysis, you got to go back to your experts, because remember, they've seen it all. All right? But also the modeling part itself is part of the analysis. All right? Remember, models are nothing more than another hypothesis. You assume that this is going to describe this behavior. And if it does describe it, you know what's in the model, so you can say, okay, this is the fundamentals that's causing this behavior. If it's not capturing that, you go, well, I know what this model captures, and I know what it doesn't capture, so it must be something else that it's not capturing. And so I can actually go through that deduction with that. All right? So that's a very important thing. So I think a lot of times I see people use CFD, and then they say, oh, it doesn't work, and they walk away. And that's not really the best way of doing it, because there is an answer in there. It's not an answer that's going to get you promoted, but it is an answer that may help you solve a problem, which will get you promoted. All right, then you have to go and say, okay, given all the analysis, you look at your hypothesis and you say, is the hypothesis correct? Right? And it may not be. And that means I have to start all over again. All right? That's the scientific method. Okay? It's called research for a reason. All right? But anyway, that's kind of how we do this. Integrating our experts in the modeling with the experiments and not just doing the experiments blindly is what makes us do the research quick, fast, and despite what Raj said earlier, inexpensively. So let's take a look at this a little better. So this is a classic example. We had a problem in PSRI. This was actually done back in 2006. And just to let you guys know, maybe I'm the oldest user of Barracuda, right? Possibly? I mean,
By age or number of years?
yeah, both. Because I used it back when it was Arena Flow.
Did we need the mic for that?
Yeah, I used it back when it was Arena Flow, actually. So, and I have a nice Ken and Dale story about all this. But anyway, we had a problem with our jet cup. So we had our attrition results from, we were running a large-scale fluidized bed, and this is the attrition index that we were getting from our jet cup. And these are 6 different catalysts, and we weren't even lining them up right in terms of attrition. Forget about getting the right attrition rate. We couldn't even rank them in terms of the attrition properties. And so we said, what's going on here? So the hypothesis was that, you know, the particles are accelerating in this jet, and in a jet cup, the jets are very, very small, so they're not really accelerating to anything meaningful. And so we need to understand what the particle velocity really are to help us relate that to what we see in the larger units, right? So fine, we did this as CFD, and we ran this as Barracuda. There's a simulation. I looked at it, I said, all right, I'm already stuck. According to Barracuda, half the material in the cup's not moving. All right, and I have to admit, I called Ken up and I said, your code's crap. It's not giving me the answer I want. And Ken gave the right answer. He said, how do you know it's not moving? Now, there's a little bit of history here with this jet cup, and that is, it's been around since 1980. All right, so this is 2006. So more than 25 years, people have been doing experiments in this jet cup. And I'm like, how could it not be moving? I mean, this is such a flawed technique. So this is one of the first things I did when I started PSRI in 2006, and I'm like, one of the nice things with PSRI is by the next day I had a jet cup made out of acrylic, I had cameras ready, I was going to take video and show Ken, and lo and behold, okay, half the cup's not moving. So, hypothesis needs to change, all right? Go back to there, new hypothesis. Perhaps for an attrition measurement, particles should be moving, all right? So, and so we worked with that. We looked at a bunch of different designs in that system. Now, I'll be honest with you, we actually did this with the plexiglass or the acrylic components because we could build those in less than a day. And back then, Barracuda, it was going to take about 2 or 3 weeks. So sorry. But we came up with this conical design. And so we did say, okay, we have a conical design now. We looked at it and we go, problem is, am I looking at the same thing? Now, if you look at attrition, there's 2 mechanisms for attrition. There's fragmentation and there's abrasion. Now, typically, you think you're in the abrasion region, but if for some reason my conical cup puts me in a fragmentation region, I'm no longer comparing apples with apples. I'm comparing apples with oranges. So the best way to do that is we ran the CFD again for the conical cup. We saw no difference in the maximum velocity. All we saw was more trauma, all right, which means more particles hitting each other. All right, so basically because all the particles were moving, they were actually hitting each other. And when we actually go back to the test, and we actually tested this with respect to the large unit, lo and behold, everything lines up very nicely. All right? So this is something we would never have come across if we actually didn't try to look at the fundamentals with meaningful codes that helps get us there. Here's another one I think is very interesting. This is called gas bypassing. So there was an article that was in the AICHE. Jan Wells was actually one of our technical advisory folks at PSRI. And he said unusual hydrodynamics that he found in an FCC regenerator. He wrote a AICHE preprint and gave a paper on this stuff in that system. And the hypothesis was it's probably a poor grid design. Now, in the world of fluidization, really have to have a pressure drop that's probably at least a third of what is across the bed. If I don't, then the hydrodynamics of the bed dictates where my gas comes out, not my grid or my sparger. So we did that. We did a lot of that because when we put the right design grid in there, we still saw a lot of this gas coming off this one side. All right, so this is a 3-foot diameter bed. It's a pretty tall bed. Now, and of course, we started going through, well, was Jan's regenerator, what kind of, it was an old regenerator, Mark IV. They tend to have very tall beds. So we started putting it all together and saying, that's interesting. So we started playing around with the bed height. Okay, so we gave up the 11, we actually did 11 different designs. And we're like, yeah, something else is here. And we found it was directly dependent how tall the bed was. All right, so hypothesis basically here is that it's not a poor grid design. We're missing some fundamental hydrodynamics. Now, guys, this was just done like back in 2003. All right? You think with fluidization we'd have a good understanding of this thing, but it is a large-scale phenomena. All right? And what's different is that I could have perfectly running fluidized bed as a pilot plant, and then when I build a larger scale commercial unit, all right, I could actually get this gas bypassing. And so this was very concerning. So we started studying this a lot, and we started to use CFD to help study it. We were able to replicate it. We were actually even able to control it in a fluidized bed, but what is the underlying mechanism that causes that? So here's very interesting. This is the maximum height I can have in my bed before I see gas bypassing. All right? And this is the percent fines in that bed. Fines being defined as particles smaller than 44 microns. All right? So when I have 4% fines, all right, and a lot of the older FCC units tend to run pretty low on the fines, all right, I can get up to about 1 meter or 3 feet high a bed before I start seeing the gas bypassing. If I go to 10% fines, I'm up to 12 feet. All right? Dramatic differences in bed behaviors by small changes in fines. Oh, by the way, this is the difference in particle size distribution between 3% and 9% fines. All right? So you're not going to get this with a two-fluid model. All right? But Barracuda looks at the whole particle size distribution. It has a compressibility model in it too, which is also important because that's a driver here. And so we said, well, let's look at this with Barracuda, and maybe we get an understanding. Barracuda actually captured this very well. It actually even captured the transition from going from non-gas bypassing to bypassing. It did a remarkably good job there. That gave us the confidence to really explore what was actually going on. It turns out the gas just wasn't getting in the bed. And it all has to do with the idea of how do we look at a particle size distribution? We like that nice Gaussian distribution, right? The peak, okay, which is by mass or volume. In a fluidized bed, and apparently with also Barracuda, they care about numbers, all right? So if I have, you know, let's say 9% weight percent fines in my bed, I got 40% fines by number in my bed, okay? The hydrodynamics in that bed are ran by the fines. They're the manifold that's moving the gas into the bed, okay? If I don't have enough of that, my bed gets very compact, it gets less permeable, and therefore it just takes any kind of instability to cause a chain of fast-moving bubbles, which we call gas bypassing. So now, we understood this, we can say, how can we fix this, right? Adding more fines, some people's cyclone systems aren't really designed to handle this. You add fines, they just blow right out. Okay, going to a smaller bed is also kind of hard to convince people, but adding baffles seems to help a lot, all right? And we actually were able to even figure out how fast the spacing of the baffles needed to be, everything else by looking at the CFD modeling and understanding what's going on with that system here. So we understood what was going on, right? We understood that everything, you know, even though we look at all our particle size distributed in terms of weight or volume, it's a numbers game that we really need to worry about, okay? Okay, we looked at the pressure ratio for gas bypassing. We actually understand when and when it does not happen based both on modeling and experimental work, and we teach that, okay? We have that there. We have tools in there to predict that and everything else, all right? And we have a solution to get a workaround there. You can increase your fines, or you can add baffles, okay? The next thing we did was looking at internal strippers, all right? This is a little bit different here. This is a project Alan was actually working on, all right? We want to understand what's going on with strippers, all right? So our problem was strippers can flood, okay? What happens is when they flood, I get very poor mass transfer. They're no longer stripping, all right? So you don't want that. And the hypothesis was, there was some work that was done a long time ago by Richard Sr., is that the holes, you can put holes inside your stripping elements and you would actually get better stripping or better, you can have higher circulation rates before you see the flooding. And he's right, you could. He also said it was because it was showering particles through the holes. And ours didn't make much sense because the holes are only this big and particles don't like to go through tight spaces. So we thought, well, maybe it's because it's more of a control release. That was our hypothesis. So we ran that as a CFD. We ran it with and without holes to understand what was going on. And sure enough, we came up with the idea, yes, it's a control release of gas. Okay, Barracuda confirms that. All right. We looked at more than disc and donuts, though. We started looking at other types of elements. So Alan, you had to look at structured packing, disc and donuts, and then chevrons or tents in that system, which are the more common internals that are not, that don't need to be licensed. All right, you saw Raj talk about structured packing, right? Because he wants you to pay an ungodly amount of money to get that license. But nevertheless, we said, okay, we understand this makes sense. All right, it gives us something we can understand. All right. What does it do with tents? Now, these experiments, Alan was doing this in a 3-foot diameter stripper. We did it in a 2-foot diameter stripper and found out it did not relate to industrial practices. Okay, we had to tear that down and put a 3-foot diameter stripper. Okay, how much did we spend on you, Alan? Yeah, $260,000. How could you forget that number? All right. And so we put in a bigger stripper in this system. He was able to map out where all the gas is going and everything else like that. That's great. Okay, now chevrons or tents tend to have holes in them by default. Disc and donuts, not always. So the question was, we don't need to run it without the holes, until one of our clients says, oh, wait a minute, we have holes. we have no holes, sorry. And so we're like, all right, so that would have been a very expensive done, but the client was very happy with the Barracuda results, so we just actually ran that simulation, okay, to show that the difference behaviors we see with and without holes was consistent that we saw with the disc and donuts, all right? And that saved a lot of money. We actually leveraged modeling to help us get to where we needed to go. So it's not just a tool to reduce my number of experiments, not just a tool to do analysis. I can leverage it, once it's validated, to be more predictive. All right? And so, of course, then we have all this data, which we teach. We have quite tutorials on this, including webinars. and as well as probably spend about a half a day on it in our seminar, and we have lots of reading material in this area, okay, on how to design strippers. All right, the next thing I was going to talk about is the eccentric cyclone tubes. Now, if you were at our PSRI technical meeting this week, this is what I was talking about. Okay, there's a nice article by Mushkanelitz, father and son team. They talked about skewing the outlet tube over a little bit, and they get much better performance out of their cyclone. They've actually applied this for large cyclones and combustors, so there's some merit here. So that was the hypothesis. Okay, and so we're now currently actually running this in what we call research space. We're looking at a bunch of different designs. First of all, we confirmed, yes, it is able to actually show that we get better collection efficiency when we do that skewing. It even showed us why that happens. We even played around with other different configurations to do that. Now we're at the part of saying, all right, we know what we need to do. We know, instead of just blindly moving this thing around to figure out what's going on, we can actually just pin it down to a couple different experiments, which we're going to be doing, and we're going to get there. Okay? These things are blank because we just haven't done it yet. So, but we're going to get there with that. So that's our research process. Okay? But there's more. I mean, we do more than that. There's also other things we have to worry about at PSRI. One is reliability. Okay? And that is class sample. Okay? That, because the class samples, some client or clients come to us saying, this is a problem. What's going on here? How can we get around it? Okay? In other words, I can't keep my unit running as long as I need to keep it running. All right? So, you have a historical perspective. What's the history? Is this something new? Has it been going on for a while? Where is it happening? Experts, okay? Then you get the experts together and develop the hypothesis. Then you work on the research. Now, the research could be experimental or experimental and modeling, etc., okay? Kind of replicate what's going on and then come up with an analysis of it and then figure if the hypothesis is correct. Now I have a solution. Teach it, understand it, basic stuff, okay? What does this actually mean? Here's a classic example. So there was this result that came out in 2006 that clearly showed for fluidized cat crackers, the number one problem for keeping that unit up and running were cyclones, okay? Cyclones in the reactor, cyclones in the regenerator. All right? The problem was huge amount of erosion in the secondary cyclone in the cone region. So the hypothesis was, we had a historical perspective associated with this, and Shell, right, they have this vortex stabilizer. They actually came to us saying, you know, we don't have this problem. We'd like you to look into it because we know it works. We just don't know how it works or why it works. All right? So we had Shell's blessing to look into this. This thing's been around since 1989. Shell was smart enough to pick up in 1990. Now, a secondary cyclone in the FCC area, if you get maybe 5, 6 years out of it, you know, without even patching it, you're doing great, okay? Shell has secondary cyclones that are more than 25 years old, all right? So there's something here, all right? There's some video of a cyclone, secondary cyclone, and you can see we're doing this thing without this vortex stabilizer. Our vortex stabilizer is just, we're using a flat plate. I was going to put this in a commercial unit. It'd probably be like a conical hat. But we use a flat plate because we don't care. And it's about a third up. You have an annular gap that goes around it. All right? And the idea was it's supposed to stabilize the vortex. Well, here's what we're looking at here. You can see why you have erosion in this region here. All right? You have a lot of swirling. Primary cyclones, you only see about 1 swirl, maybe 2 swirls. Secondary cyclones, lots of swirls. And that's rubbing right down there at the bottom. You can see why you have that erosion problem. This is with the vortex stabilizer. So something's really happening there we want to look at. We did a lot of research in here. So this is actually, we put a plaster coating on the inside of the cyclone. All right, we actually ran it longer than you would ever run it just to show that you get the same type of erosion pattern, okay, before and after. What we usually do is just weigh the cyclones before and after, and we can actually quantify how much erosion is happening. This is our standard control design. This is the actual vortex stabilizer. And then if you go to a cyclone vendor and complain about cyclone erosion, they typically give you these things called dust hoppers, which I can't stand, and because it just makes it harder to repair your cyclone. All right, and they are right. It did seem to reduce erosion, but they're more expensive and they're harder to fix. The vortex stabilizer reduced erosion by 5x. My cyclone lasted only 5 years. I can get 25 years out of it. All right, huge significance. All right, we've been working with this vortex stabilizer for a while now. It has other advantages as well, which CFD has actually helped us with, but I'm not going to talk about that. What I am going to talk about is why is this working, all right? And the hypothesis that it's stabilizing this vortex, this inner vortex in the cyclone, is not really correct. What it's doing is it's changing the vortex just below in the bottom region. It's reducing the amount of swirl slightly. Now, erosion tends to be a function of the angular velocity of the square cubed. Small changes make a big difference in erosion, and that's all we're doing here. All right? And that's the beauty of it. That's why I don't really see my grade efficiency being hit that much. All right? And that's why we actually see a pressure recovery, so I can even use shorter dip legs with these cyclones. All right? For once, Mother Nature has given us something that it's not painful to implement. All right? So that's kind of it. So with the CFD, we developed an understanding. It changed our hypothesis. All right? And then we actually now teach this. We have tools on how to design all this stuff, and we have lots of papers in there to help solve your erosion problems with respect to the cyclone. How much time do I have? Am I going too far?
-2 minutes.
Okay, I'm almost done here.
But this is really good.
Okay. The next thing is the PSRI design and scale up process. Okay? Same thing. All right, you have a problem. That is, I have a small concept here. I want to make a big plant here. That's called scale up. All right? It goes through a design. Okay? That's where your experts come in. All right? Okay? And now you have to say, what are my design parameters I need to worry about? This, the scale up parameters that are scary. Okay? You have to understand that. The experts are also very important there. You also start doing cold flow studies to understand what those parameters actually mean. So, classic example, the gas bypassing problem. How deep can I, with this particular catalyst and the particular system I have, how deep of a bed can I have before I think I'm going to have a problem? If I am going to have a problem, I'm going to spend a little bit more money to put those, the internals inside of it, the baffles. All right? Then you go through the analysis with the modeling, because cold flow gives you a good understanding of the hydrodynamics, but it's cold flow. All right? Your process is not going to be cold flow, and it's not going to be with air or nitrogen. It's probably going to be with some reactant at a higher temperature to make a product you want. Our product is just more air, or the same air, just a little dirtier until it gets to the baghouse. So, okay, you have to bridge that gap, okay? Now, going to higher temperatures, going to different pressures, using different reactants, okay? That's changing your drag, all right? Now, we can do that with cold flow. We just adjust the velocity to match drag, but we're going to want to use CFD to really make sure we get there, all right? The tool is mature now. It can actually be a useful tool for scale-up, all right? I'm not sure I'd make it my only tool, but it certainly would be one of my important tools for this area, all right? Is my design correct? The experts look at it. They look at the modeling. They look at the experimental results, and they say, yeah. Now we can go through the solution. We understand what we're doing, and now we have to teach that, especially those that have to do further design and further operations of the system. Now, we also have to worry about, with respect to our modeling, you have a preliminary model. That's the quick and dirty thing to make sure you're on the right page. You look at the fitting parameters. Now, you're going to want to validate this, all right? Unfortunately, some people call CFD a fundamental model. It's not, all right? There's a lot of empiricism in there. You're going to have to fit it. You've got to find the right, I think someone this morning, I forget who it was, talked about finding the right data. I think it was the student from Denmark. Find the right data to actually validate your code, okay? It's going to require some fitting. If you use the EMSS model, okay, that little algorithm you use to get those parameters is actually based on kind of a similar concept, all right? So you have to fit it. Now, if it's a fluidized bed, we like to look at bed density and entrainment. All right? So you have your fitting problem. And now I can develop my large-scale model to extrapolate from what I know to the unknown. Okay? It's still a risk. All right? But it's better than the wild guess that we used to do. All right? You got to make sure it's validated. There's another part you need to worry about. Okay? It's called process risk analysis. Take your design and sit there with your room full of experts, all right, and say, what could go wrong? And if it goes wrong, where is it going to hurt? So you may have to look upstream and downstream and everything else like that, but if you don't go through this process, you're going to build this plant, something's going to go wrong, and it's going to cost you twice as much money and twice as long to actually fix it. And that also could involve some of the modeling. Your large-scale model can be a very important part of that, okay? Like fines. Oh, if my fines level drops below 4%, I'm going to have problems, okay? What are those problems going to be? I'm going to get gas bypassing. Well, what's that going to happen? Well, gas bypassing could shut down the cyclones in my regenerator. All right? That could dump a lot of solids downstream. Can I handle that? All right? If you can handle it, You know you don't want it, but it's not as critical. So that's the 3 steps that we typically do in terms of looking for the scale-up. And finally, there's the retrofitting, right? You have an existing plant, and you're saying, look, I just want to make it better. I want to do it as fast as possible, as cheap as possible. All right, so you go through kind of a similar type of analysis here. Process risk is also very important in that, and you still probably should develop a large-scale model to get you there, because it will help you understand better what you're implementing and what some of the risks are associated with that. So, path forward, same thing, problem hypothesis, use experiments and modeling to help define your research space. Use experiments and modeling to help to understand what's going on here. Now it's going to be a little bit different, okay? Artificial intelligence is actually coming into reality, all right? And the idea here is now I can actually, and there was a talk by the NATL guy, I forgot what he called that code. What'd you call that, Jason? NodeWorks, yeah. All right. I know the Siemens folks has something called HEEDS as well. Basically, you can actually take these codes and you can put it through some sort of objective function. This is the answer I want. I want to solve onto this. All right. This is what I can change. And it'll just run this in a continuous loop, making smart, educated guesses on how to do this. All right. So you can use some numerical technique like simplex and everything else, but artificial intelligence will get you there faster. To the point now, because CFD takes a long time, I don't want to use the simplex method. That's really painful. All right? Artificial intelligence will make that actually achievable. So you're going to actually now see us having more refined solutions by actually integrating CFD with the artificial intelligence, with experiments and cold flows, validating what's going on there in the whole process. It would be a good recipe for success. So that's my vision of where we're going in the future. So in respect, okay, doing this kind of work involves experiments, it involves modeling, it involves experts. I don't think you can remove either one of those.